in this chapter, we're going to talk about organic reactions. And I have an image here for you, and it's from one of my kind of favorite scientists/artists, which is Andy Bruning. And this shows the functional groups and common reactions that are used to convert between them. And we're going to be doing some of these reactions as we go through the rest of our journey together with organic chemistry. And so understanding how to transfer or change from one functional group to another functional group is very helpful in planning multi-step syntheses, or, for example, synthesizing natural products. You're going to see here there's a reaction key, like addition and substitution and elimination. You're probably already familiar with oxidation and reduction. And so we're going to go through and introduce some of these reactions in this chapter, and then the rest of these will be introduced at some other point in your journey through organic chemistry. So before we do that, we need to go over some basics of organic reactions. Now, when we talk about organic reactions, right, virtually all organic chemical reactions are really going to be woven together by a few basic themes. And here's the pattern that you're really looking for is you need to identify things that are electron rich, right? And then you need to identify things that are electron poor, right? Because things that are electron rich, right, things like partially negative or have a negative, or things that are like nucleophiles, are attracted to things that are electron poor, which are going to have a partial positive or a positive charge, or are electrophiles. And you will see this pattern over and over and over again. Now, let's look at different ways that we write organic reactions. An equation for organic reactions is usually drawn with a single reaction arrow between the starting material and product, even though we know that there's an equilibrium that can be established there. You can write the reagents either with the organic molecule or above the arrow. It means the same thing. The other thing that you're going to see sometimes with these reactions are going to be reaction conditions. H nu is light. The delta here indicates heat. The solvent a lot of times is written below as well. So reagents tend to be above and reaction conditions tend to be below the arrow. So reagents above, reaction conditions. And some things you'll even see go as so far as to show you the actual temperature, right? So it'll say, negative 78 degrees or whatever. The other thing that you're going to see with organic reactions are sequential reactions. So if you have two sequential reactions that are carried out, you're going to see steps. So for example, the first step is here above the arrow and the second step is below the arrow. These are not reaction conditions. Okay, these are steps to the reaction, and it says, hey, look, you do this one first, you stop and you do some sort of workup, and then you're going to do this reaction next. The other thing to notice here is a lot of times these are not going to appear to be balanced because the inorganic byproduct is a lot of times omitted, right? So just kind of watch out for that. The next part of this screencast in this chapter, we're going to look at some common organic reactions. So the first organic reaction that we're going to look at are substitution reactions. And this is just a reaction where an atom or a group of atoms is replaced by another atom or group of atoms, right? So in a general substitution reaction like we look at here, right, we have Z, which is our generic heteroatom that shows up a lot, right? Something that's not carbon. And we see that it reacts with Y, and that Y will come in and replace the Z on the carbon atom. This is an example of a substitution. One thing substitutes for another. That's it. Now, substitution reactions often involve sigma bonds, right? We have one sigma bond that breaks, and we have one sigma bond that forms at the same carbon atom. So one sigma bond breaks, and one sigma bond forms at the same carbon atom. Okay. Now, some cases this Z here can be a hydrogen atom, but the most common examples that we're going to see are where it's a heteroatom that is more electronegative than carbon, like oxygen or nitrogen or a halogen. Here's an example with a halogen. We have a hydroxide group here. It comes in and it attacks this carbonyl carbon, and it replaces the chlorine there. And so the hydroxide group substitutes in for this chlorine. Now, we also have elimination reactions. In elimination reactions, this is just a reaction where elements of the starting material are lost and a pi bond is formed. So, right, elements of the starting material are lost and a pi bond forms, right? So what we see here generally are kind of two groups, and they have sigma bonds. You add a reagent, and all of a sudden you have a double bond where a pi bond has formed here. It's not always a double bond. Sometimes it's a triple bond, but you're forming a pi bond. One of the examples that we can show here is the loss of water, where we've got an OH group and an H. We're going to add sulfuric acid as our reagent, and we form a new pi bond. Water is our byproduct there. The next reaction we're going to look at is an addition reaction. In an addition reaction, this is just a reaction where elements are added to the starting material. Right? So we have some sort of pi bond, and that pi bond is broken, and two sigma bonds form. An example of this is if we were to take that alkene on the previous slide with the double bond and add the water back with sulfuric acid, we end up with an alcohol functional group here. When we look at this, as you can kind of already tell, what I've hinted at is that elimination and addition are exact opposites. So a pi bond is broken, right, in a addition reaction, and then it is formed in an elimination reaction. Often these reactions are reversible. All right, so often we see that these are reversible. Now, one of the things that I enjoy in organic chemistry is knowing exactly what happens, right? Not just memorizing that, okay, hey, look, we have a double bond here. We're going to add this and it's going to go over here. I like to answer the question why and how. And so the big question here is how? How do we go from this to this? And one of the things that can help us with that are reaction mechanisms. Now, a reaction mechanism is just a detailed description of how bonds are broken and formed as that starting material is converted into product. Okay. A reaction can either occur as one step or a series of steps. A one-step reaction is called a concerted reaction. Right? And we can see a schematic here where you have reactants and it goes to products. Okay. And so the idea here is that no matter how many bonds are broken or formed, a starting material is going to be directly converted to a product. Now, a stepwise reaction is one that involves more than one step. Right? And so you have you have some sort of reactive intermediate, which then goes on to form the product. So the reactive intermediate, when we talk about that, it's generally some sort of unstable intermediate that goes on to then form the product. So let's look at a few ways that bonds can break and form. Regardless of how many steps there are in a reaction, there's really only two ways to break a bond. That's it. Okay? The electrons in the bond can either be divided equally or unequally between the two atoms of the bond. So, breaking a bond by equally dividing the electrons between the two atoms of the bond is called homolysis or homolytic cleavage. So this is just breaking a bond by equally dividing the electrons between two atoms, right? So what happens here when we do this, when this goes through homolysis? One electron, so there's two electrons that make up this bond. One electron goes on the B atom here, and we're going to show this with a one-tailed arrow, just like this. And then the other electron goes on the A atom here, and we show it just like that as well. So homolysis, a few things about this. Homolysis generates two uncharged species with unpaired electrons. Okay, so we end up over here with two uncharged species with unpaired electrons, an unpaired electron, right? I want you to remember we talked about this before, but these are called, when they have that unpaired electron, are called a radical, right? And so that's just that reactive intermediate with a single unpaired electron. Now, radicals are highly unstable. right? Because they contain an atom that does not have an octet of electrons. Now, what we are going to see more often, though, is heterolytic cleavage. And heterolytic cleavage is just the bond breaking by an unequal dividing of electrons. Right? And so when we look at this, when these atoms have different electronegativities, the electrons end up on the more electronegative atom. And so, depending on how the heterolysis goes, it's generally shown like this, where you have your A and your B, and you have your bond there. The arrow starts in the center, and let's say that B is more electronegative. Those electrons then go directly on B, okay? Then we show, right, that A has a positive charge, and B now has a negative charge. So if these are carbon atoms, right, then we generate a carbocation. So a carbon atom with a positive charge is called a carbocation. And then if these are carbon atoms, we generate with this negative a carbanion. And that's just a carbon atom with a negative charge. A carbocation is generally an unstable intermediate, and that contains a carbon surrounded by only 6 electrons. And then the carbanion is a unstable intermediate as well, and it has a negative charge on the carbon, which is not a super electronegative atom, which is why that tends to be a little bit more unstable. Now, I hope that you notice that I'm really emphasizing where I start these arrows. The details matter here when we're doing mechanisms. So here's some things that I don't want to see, right? I don't want to see atom movement, right? Something like that. That's wrong, okay? Make sure that your arrow starts where your electrons are. Okay, and so if that's a bond, it's in the middle of the bond. I also don't want to see just drawing an arrow off into space somewhere, right? You need to show, so it's mechanisms to chemists are a lot of times like stories, right? And the arrows tell us things. The arrows tell us that these electrons go onto this atom and it forms a carbanion, and then using that information we can go on and figure out how it reacts. We can continue the story. This doesn't tell me where the electrons go, so I can't figure out where the story is going to continue on, and so that's incorrect as well. So we are going to work on this in class, but you really have to pay attention to the details. You must be detail oriented here. Now, homolysis, and as we mentioned, homolysis and heterolysis here are going to generate the 3 most common reactive intermediates in organic chemistry: the radical, the carbocation, and the carbanion. Radicals are intermediates in radical reactions. Most of those are going to pop up in organic too. What we are mostly going to be interested in are these ionic intermediates that are seen in polar reactions. Now, we've talked a lot about how bonds break, but let's also talk about how they form. That's the other kind of part of organic chemistry. So bond forming occurs in two ways. The first way is that two radicals each donate one electron. Okay, and that forms a 2-electron bond. So let's look at that. Okay, you have your happy radical A, you have your happy radical B, right? One electron goes here, one electron goes here. Oop. And we'll put a positive sign there. And now those two electrons have formed a bond, just like that. One electron comes from each atom. The second way that you can see that is that you can form a bond is that you have two ions with unlike charges that can come together. Right? With the negatively charged ion donating both electrons to form the 2-electron bond. Right? Now, an example of this would be if we have A as our carbocation and B, let's say it's our carbanion here, right? And we are going to start the arrow there at those electrons, and we're going to say, hey, look, they're going to come over here to A and form a bond, okay? And there in red is our new bond. Bond formation always releases energy. Right? Bond breaking always requires energy. Bond formation always releases energy. And whether the overall reaction is favorable or not is based on many factors, but one of those factors is how much energy it requires to break the bonds of the reaction and how much energy it requires to form the bonds of the reaction. So those two ideas are always at play. Now, we've used a lot of reaction arrows, and so I love the summary table in your textbook. It shows, hey, look, this right here is a reaction arrow. It's drawn between the starting materials and the products in an equation. This is a double-headed reaction arrow. Those are equilibrium arrows, right? So it's drawn between equilibrium equations. This is a double-headed arrow. This is resonance structures. A full-headed with two prongs curved arrow is going to show the movement of electron pairs. If you have one prong, it's called a fishhook. And and it always shows one electron that's moving, okay? 2 electrons, 1 electron. You're going to see people going back and forth between this. Pay special attention if there's a double-headed arrow, because a lot of times that does imply equilibrium. All right, this finishes our first screencast on organic reactions. In the next screencast, we are going to talk about some thermodynamics. Yay! As always, if you have any questions, please feel free to stop by my office.